This is Module 11, where we will cover cubic yard as a pay item for structural excavation, trench backfill, structural concrete, and drilled shafts. On the doc guide, page B as in Bravo, B1, you will find the requirements for cubic yards, accuracy of measurement, and the documentation required. There are a number of pay items that are paid for by the cubic yard, such as structural excavation, trench backfill, porous granular embankment, concrete structures, drilled shafts, and then concrete outlets. Anything to do with concrete is measured to the nearest tenth of a cubic yard for pavement. Individual dimensions are to be at least to the nearest tenth of a foot. All other items can be measured to the nearest 0.1 cubic yards daily, and the final quantity summarized to the nearest yard. The reason for this is concrete items tend to be rather pricey, so we go to the nearest tenth of a cubic yard, and items such as porous granular embankment, which are low value, can be rounded to the nearest cubic yard. Required documentation is to present your measurements and calculations. You can use the statement built according to standard or built according to plan on the sheet details. Just fill in the blanks here with those details. Or possibly use Form 891, which is the plan quantities with daily calculations for estimates. If there's a thickness associated with an item, especially items that are built according to a standard, like a concrete outlet may have a certain thickness, you would have to do some depth checks. Let's go to the standard specifications and item article 502.12, which is the method of measurement for structural excavation. Give you a minute to find that in your spec. Here's a little bit of an excerpt on it. Again, we can build according to plan and pay for it that way. 20207A is reference, so that allows that to be done. If you're measuring quantities, there are some limitations on what you would pay for in the quantities. Basically, the horizontal dimensions will not exceed beyond vertical planes 2 feet outside the edge of the footing of the bridges, walls, and corrugated steel plate arches. So basically, whatever excavation you do beyond the footing, you can only pay up to 2 feet, and we'll cover this a little bit more detail. Here is a foundation being prepared for a mechanically stabilized wall, MSE wall. Notice that there has been some excavation beyond the footing. This would be the formwork for the footing, which would rest in here, the other side of the formwork. And it appears to be a little bit more than 2 feet, but according to our specification, we would only pay for 2 feet beyond the edge of the footing. Just another picture as the work progresses. We now have our rebar in place. Some additional formwork here to stabilize the foundation wall for that pour down here. And here is the completed wall. Let's go to an example of an IDR for structure excavation, which is on page F45. Here we have our normal heading information and the work being done by various people here. We would have our job stamp. Under 502, which refers to structural excavation, we're at Pier 2, and we have a station on that. And how many cubic yards of earth excavation for this structure was conducted. Notice that we don't have anything in here for evidence of material inspection. That's because it's a removal item, so there's no material to be inspected being incorporated into the work. Always note that this will be a final field measurement because it's a removal item, and it's the only opportunity you're going to have to measure what was removed. So the contractors conducted his work, and we know our footing is here, so it's been drawn on the IDR, and then the dimensions that were excavated beyond that footing, and then the total excavation and width lengths are given, and then the depths at the four corners of the excavation. So to calculate a volume, we average all the depths. So that's what this does. So all these depths are averaged. And then we determine the footprint of our pay area. Notice that we're within 2 feet here and 1.6 feet here. So that's exactly what we can pay for, to 75.6 feet. Width-wise, we went 2 feet and 2 feet beyond the excavation. We can pay for that as per specification. So that's 12 feet. So those two dimensions, and then divide by 27 cubic feet per square yard, or cubic yard, I'm sorry, gives you the 239.4 cubic yard. These measurements came from a field book, so those are referenced. Field book number 3 and what page for this layout. Let's go to workbook page 7 and perform this problem. Just a few hints. Remember what our spec requirement is on paying up to 2 feet beyond the footing. Let's see what we have going on here. So with that hint, perform your calculations for the cubic yards of structure excavation. Okay, if we go to workbook page 29, we'll see our solution. Again, the reminder of the Article 502.12, that horizontal dimensions will not extend beyond vertical planes 2 feet outside the edges of the footing. That was that hint. So if the contractor did not excavate to the 2 foot limit, do not pay. You cannot pay the contractor for work they did not do. Therefore, the pay dimensions are as follows. So the length, we had 1 foot plus 32, and then 2 is a limit. Width-wise, 2 plus 10 plus 2, which are the limits. So we got 14 by 35, and our average depth was 5 feet. So we simply multiply that together, divide by 27 cubic feet per cubic yard, and we get 90.7 cubic yards. Let's talk a little bit about trench backfill. In your documentation guide, in section E is in Everett, you will find a series of trench backfill tables. These are very handy to use. They're for concrete pipe, so they only work for concrete pipe because the wall thickness is taken into account in these tables. It assumes that the trench width is the maximum allowed. With depth, the trench has to be certain widths, and if that trench is that width or wider, then these tables work for calculating the trench backfill as presented in section E. Let's talk a little bit about the trench backfill material. If you're away from the roadway or a sidewalk or any other type of structure, it really doesn't matter what type of material you put back in, as long as it came out of the trench, you can most likely put it back in the trench. However, once you get around the pavement or curb and gutter or sidewalk, we want that to be a stable environment. We don't want any long-term settlement over that piece of pipe that had that backfill. So as a result of that, we have a requirement under 20801 that the aggregate for backfilling trenches made in the subgrade of a proposed improvement and all trenches where the inner edge of the trench is within 2 feet. That's the critical dimension here, 2 feet of the proposed edge of pavement, curb and gutter, stabilized shoulder, or sidewalk. So any of these common pavement, sidewalk type elements requires that an aggregate be used for backfilling the trench area. When trench backfilling around drainage structures, be aware that under like section 602.12, some of this has already been made incidental to that work. For example, if you have a manhole, the excavation shall be made to a diameter of at least 6 inches greater than the diameter of the structure. So if you have a manhole at least 6 inches beyond that, diameter-wise, will be backfilled as part of that work. So that is incidental to that manhole. We don't want to pay for that backfill twice, so we will have to deduct that from our trench once we get into that calculation. So likewise, if that structure is within 2 feet of the pavement edge, then the backfill material will need to be either sand or stone screenings. Let's go to section E of the dot guide and review E1 through 5. First of all, these tables can be used by the designer or field engineer to determine the volume of trench backfill that can be paid for storm sewer trenches. Again, this must be a concrete pipe to use these tables, and the trench must be wider than the minimum width. Let's go to page E1 of the dot guide and talk about the conditions needed to use the trench backfill tables. First of all, let's notice the depth of the trench itself. There's a key factor of 5 feet. That controls the pay width that we will pay for on the width of the trench. So if it's a shallow trench, 5 feet or less, we will pay an aggregate backfill width of the diameter of the outside of the pipe plus 9 inches on each side. So that's our maximum pay width. This width max is a little bit of a misnomer. It should probably be renamed maximum pay width of trench. The trench can be wider, but that is the maximum width we will pay. Now, if the trench is more than 5 feet, you're probably going to have some sort of protection included in there to protect the trench from collapse and protect the workers. And that's being recognized. So there's a wider pay width of 18 inches plus the outside diameter of the pipe. So 18 diameter of the pipe on the outside plus 18. To utilize the tables, there's a thing called D, or the depth. That is measured from the invert of the pipe or the flow line to the surface of your excavation. By doing that, that will tie into the haunch thickness, haunch elevation above. So this is the area that we're going to calculate in the tables for trench backfill. Included in the price of the pipe is already this backfill on the underside below the haunch, roughly 4 inches below the pipe to the bottom of the trench and around to the haunch. So that's all included in the cost of the pipe itself as incidental. And then we are paying basically from that haunch up to the surface in the trench backfill. Here's a slide that shows another way to explain what's being paid for in this pay item. It's the hashed area. So below the pipe and around up to the haunch, and any extra width beyond the 9 inches, if it's below 9 feet or 5 feet. If it's over 5 feet, we're going to go wider to allow for some protection. And the diameter of the pipe another 18 inches. So this is the hash area being paid for. So the maximum width of what we're paying for is defined as 18 plus outside diameter plus 18 if it's below 5 feet. If it's less than 5 feet, it's 9 plus the outside diameter plus 9. So this is what we're paying for. And to tie into the tables is the invert depth, the D. So the check we need to do with the contractor's operation is to see if the trench width, the actual trench width being dug, is the same or slightly wider than what the formulas calculate. If it ends up being narrower, we have to go back to the actual formula and calculate it ourselves. The tables will not work. And these extra width of material is not paid for. So again, to illustrate a little bit about the trench backfill, this is the area where the trench backfill will be paid for up to the inlet structure. Remember, we got 6-inch diameter that will be included in this structure. Or if you cut that in half to a radius, is 3 inches. So on our trench backfill, we need to subtract off that 3 inches on this side, because that 3 inches is included in the cost of this structure. So minor detail, a little bit of math, but that's the way the specification is conducted. Let's look at this manhole from above a little bit. Here's our manhole. Here's our trench backfill, 3 inches included in the cost of the structure. So when we determine the cost of trench backfill, the length of this trench, typically we measure up to the manhole, but then we need to subtract off 3 inches of trench because that's already included in the manhole pay item. However, the pipe itself will be paid for all the way through the manhole and into right where it touches the edge of the manhole. So that will be your pay length for pipe, comes inside all the way into the pipe, or all the way into the manhole. However, for trench backfill and the aggregate portion, you may measure to the manhole, but then you subtract off 3 inches to account for what's already been included in the cost of that structure. This is on Workbook page 8 also. Let's go to F46 of the dot guide. Here you can see we are placing some concrete storm sewer in a trench. Here we have a few details on the cross section. From the back of the curb to the back of the curb is 53 feet. We measured the length of the pipe from manhole to manhole, which is 66.6. We also collected some information on the pipe markings, what class, date, and the mark for the production. So from the list and mark, we have our evidence of material of inspection. We have our length, 66.6 feet, and we record storm sewer 2 reinforced concrete pipe class 3, 24 inch. So we got that one taken care of. Next thing we need to look at is the trench backfill. So there's a couple of things to look at. From back of curb to back of curb is 53 feet. But then we go 2 feet beyond that on each side to make sure we have a good stable structure. So that calculation 2 plus 53 plus 2 is 57 feet will be our pay length. Then we need to do a check on our trench width. Contractor dug 5.6 feet wide. And we have our 24-inch pipe, which is an inside diameter. And we know that this is over the 5 feet to the bottom of the trench, because it'll be 6.2 plus 4 inches. So that is well over the 5 feet. So we know we got 18 plus 18, that's 3 feet. 2-foot pipe, so that's 5 feet. And then we had the wall thickness of the pipe 2 times. Well, it turns out a 24-inch wide pipe, if you take the 24 divide by 12 and add 1, that will give you the wall thickness. So that's 2 plus 1 is 3. We got 3 and 3. That ends up being 5.5, 5.5 feet in width that we will pay for. The contractor dug wider than that, just barely meets it, so we can pay for this whole width of the trench. As far as the tables go, we can use the table. And that's what was done here. Used a table. From the table, looked up 0.968 cubic yard per linear foot of pay length. Then the calculation, 55.2 cubic yard. That's what we have here. We noticed the material came from an approved source. We have our shipment weight tickets, and we're good to go. So let's go to page E3 of the dot guide, and we'll look at the table for the volume of trench backfill. If you remember, we had a 24-inch pipe, and it turns out that a rule of thumb for the wall thickness is you take the diameter of the pipe in inches, divide it by 12, which in this case gives you 2, and then add 1, and that will give you the wall thickness. So 3 inches is the wall thickness. Our D dimension was 6.2. So that's where we came up with the 968.968 cubic yards per linear foot of run that was used in our calculation. Let's go to page 9 of our workbook. Here we have a trench backfill example for a pipe running parallel to the center line of the road. We're giving a few items here, plus a nice drawing. We know we have a 42-inch diameter pipe. The average depth to the inverted pipe is 6.8 feet. From manhole face to manhole face, our run is 75 feet. We know how wide the contractor dug his trench, 7 feet 4 inches. And then center line of the pipe is 5 feet behind the back of the curb. So we're to determine the allowable pay quantity for trench backfill. Well, the first thing we should do is check to make sure that trench backfill is even required. Because if it's not required, we don't have to pay for it unless the contractor with an extra wide trench encroached upon our 2 feet. Then we would require the contractor to backfill with trench backfill material, but we would not pay for it. In this case, we got 60 inches, which is 5 feet. And we know our center line of pipe to the edge of the trench is going to be 43.5 inches, leaving well under the 2 feet. So yes, indeed, we will pay for trench backfill from manhole to manhole in this case. The next thing we need to check is what will be the length of our pay. We know it's 75 feet from face to face to the manhole, but if you remember correctly, we need to subtract off 3 inches from each manhole to account for what material, trench backfill material, is included in that manhole pay item. So that's going to be 75 feet minus 6 inches, or 74.5 feet will be a pay length. So a little more formal, here's our solution. First, we're going to do that check to see if we do need to pay. And indeed, when we do our calculation, 5 feet, 60 inches minus the 43.5, 16.5. Yes, it is within the 24 inches, so we must use trench backfill. Then secondly, what is the length? It is the 75 feet, but remember, our Article 602.12, included in that manhole structure is a 6-inch diameter backfill, so we need to subtract off 3 inches off of each manhole. So 75 minus 3 minus 3 is 74.5 is our pay length. Then our last check is to see if we can use the trench backfill tables. So we look at the allowable trench width. D is obviously 6.8 feet, which is greater than 5 feet. So we're in a situation where you have 18 inches wall thickness, inside diameter wall thickness, and 18. That ends up being 87 inches once we plug all those in. 18 wall thickness of 4.5, 42, 4.5, 18, 87. Contractor ended up excavating 88 inches, just a little bit wider than what we need to use the table, which is fine. And then we will use the table with a D of 6.8 and the inside diameter pipe of 42 inches. If you go to page E3 of the tables for trench backfill, you will find 42-inch pipe on the top, and then the 6.8 feet gives you the 1.093 value. So that's cubic yards per foot of run. Multiply that out and you get your 81.4 cubic yards. Let's go to Workbook page 12, where we have a trench backfill problem for you to tackle. This one is running perpendicular to the road. We're giving a few bits of information here. We have a 24-inch circular concrete pipe. The depth to the invert is 3.8 feet, and the contractor excavated their trench width at 50 inches. So here's that 50 inches in the trench width, how deep it is to the invert. We have a few features here. We have a manhole, a little bit of distance, back of the curb, pavement, back of a curb, a little green space, a sidewalk, and then a little space to the next manhole. So this exercise is to determine the allowable pay length for the trench backfill, maximum allowable trench width, and the allowable pay quantity for trench backfill. There is an IDR in the workbook on page 14. Please fill that out as if you were out on a job and had this information in hand in your inspection. Some additional information to fill out on your IDR is the date, contractor, the weather, pay items, station location, and show your calculations for your primary source of documentation. Here is your blank IDR to fill out. Let's go to Workbook page 30 for the solution to this problem. Again, let's look at the allowable pay length. We got 2 plus 4 plus 2. That represents the sidewalk plus the 2-foot allowance on either side of it. Then we got 53 feet, which represents from back of curb and gutter to back and curb and gutter, plus 2 feet on either side of it. That totaled up gives us 65 feet. The maximum allowable trench width, we go 9 inches, since this is a shallow trench, or less than 5 feet. We go 9 inches, outside diameter plus 9 inches. So in this case, our pipe thickness is 3 inches. So we got 9 plus 3 plus 24 plus 3 plus 9 gives us 48. So 48 inches is the maximum width we can pay. The contractor dug 50 inches, so we can pay for all the width of the 48, which also allows us to use the backfill tables in section E. And from the table, we look up 24-inch pipe and 3.8 feet for depth on D to the invert. And you should find that's 0.323 cubic yards per foot. So we simply multiply the 65-foot length times the 3.23 and get 21 cubic yards even. So on page 31, our IDR should look something like this. We have our header information that was provided, our item code, our pay item is trench backfill, the location, we calculated out the 21 cubic yards, evidence of material inspection, look that up in one of 2 locations. If you want to use the documentation guide for evidence of material inspection, it is located in C, in this case C4. At the bottom, you'll see section 208, trench backfill, and it's required to have the approved source and a shipment ticket, which is list and ticket as noted. Also, if you would like to use the project procedure guide, which is located in the appendix, in this case, the aggregate portion is located on appendix page 58. It is a granular use, and you'll notice that if you look that up, it's list and ticket. This is a final pay item, so we can check that. Include our item code here also. In this case, we did not include a drawing, but it could be included to make it a little bit clearer. In this case, we just determined the allowable pay length, maximum trench width, and then allowable to where you could use the table or not, and then what you picked off the table. So this all can be easily checked. Let's move on to cubic yards of concrete for structures. Here you'll see that concrete can be formed into a variety of shapes. This happens to be the Stan Musial Bridge over the Mississippi River, to be I-70 eventually. In the background, you'll notice here is a tower for the pier that's in the water for the cable stay that will rise up. And then we have the abutment for which it's going to land here. And then the remainder of the land bridge. Due to the size of these structures, it can be difficult to get concrete in and properly consolidated around the extensive rebar cages being used. Also, it's not uncommon that the weight of the rebar can push down on the chairs and flatten them to where there's not enough cover on the rebar. So these are things to watch out for. You can see here a lack of consolidation around this pier. And this flat area here, there's some bare bar, also some honeycombing going up through this area. These were repaired at the contractor's expense. Here's the Illinois side pier of the cable stay. You notice there's a tremendous amount of rebar in this structure. And this is where calculations and using a ratio of pounds of steel per cubic yard of concrete can come in handy in your estimate. And as you go up, estimate the amount of concrete and then final it out at the end. Just another example of the forms and bracing required to cast the pier on up. And finally, we're installing the cable stays and the deck elements. Here's an example of one of the edge beams where the cable will be threaded through and anchored for support. And here's the bridge in the near completion phase of the deck being in place, the cables being in place, and the final touches being put on before opening. Here's a bridge deck pour operation. You can see we have our concrete being delivered over here and being pumped to the deck, being spread out in front of the bridge paver. Then we have a finishing texturing machine. And finally, we're covering it for curing. You notice that there's several different shapes here, and it's very important that you have measurements that are accurate to where you can calculate these shapes correctly for payment. Let's go to your document guide, page F47. Here's an example of doing calculations for concrete structures. What is being done is each element is being calculated for volume of concrete and pounds of rebar. That way, as it's built, you can reference this calculation sheet and utilize this information for your payment. So you would estimate on the way up and then do a final once it's completed. Here's an example of a summary of your field calculations. You may have several sheets behind this with the detailed shapes, rebar, and so on, and then summarize it in this sort of a summary sheet for your project. And then this can be referenced for your payments in the future. Let's talk about drilled shaft foundations. We will not be getting real deep into drilled shafts, pardon the pun, but we will be covering enough to where you can assist with measurements, calculations, and checking of this work. There is an entire class devoted to drilled shafts. The major concern is safety around these shafts. They're basically a deep hole. You may need to utilize fall protection if water is involved, a life jacket, a hard hat, of course, ear and eye protection. Many sites have operational plans of how to gain access near the shaft, so you need to check in with the contractor and resident to make sure that you are following the plan while being positioned around these shafts for measurements and such. Here's an example of a crane-mounted drill rig. Of course, you got the crane. Here's the power unit to turn the bit. Here's an example of a bit. There are different diameters depending on what the diameter of the drilled shaft is. You may have casing involved. If it's prone to collapsing, you may have to encase the shaft or drill in slurry. Sometimes this is a pay item. sometimes it's contractor option, so be aware of what requirements are in the contract. You can have a drilled shaft solely in soil. Quite often when these are being used, you will bell out the bottom. There's a special cutting tool and then a special spade bucket that will come down and clean this area. In the case of a soil, you're relying on the end bearing to support that shaft, along with some limited shaft friction. More common in Illinois is using shafts that have a rock socket. Basically, you're going to drill through the soil and then take a smaller drill and create what's called a rock socket in the rock portion, and then that's what will support your structure. Drilled shaft plans contain a great deal of detail. In this case, we have the overall footing and then 6 drilled shafts located inside that footing to support a bridge pier. Looking at a drilled shaft from the side would be something like this. Here we have the very top, which would be the level of the soil. And then we're drilling down through to rock. So we have a top of rock elevation, and then we have a little bit of drilling through rock to anchor the shaft in rock, and then the bottom elevation for that. Associated with the design is a bill of materials, various rebar, and cubic yards of concrete. So these will need to be checked and then measured against the bill of materials in the field. Let's go to your workbook, page 25, and we have a drilled shaft problem. The goal here is to calculate the total volume of concrete in the drilled shaft per Article 516. So you'll have to go to your specification book and look up the method of measurement and the pay items. But let's review a little bit about what we have here. There's a lot of detail on the steel, but we're only here to calculate the volume of the concrete in this drilled shaft. Remember, a drilled shaft is a shape of a cylinder, right? So we need to know how to calculate the volume of the cylinder. And we have basically 2 critical pieces of information here. We have some elevations and then what those elevations represent, whether it's in soil or in rock. So go ahead and calculate the volume of concrete per Article 516, and we'll talk about it on the other side. Okay, our solution is on workbook page 42. And there's first thing we need to do is look at our drilled shaft and soil. So we have a soil portion, and we have a rock portion. So we're going to do the soil first. So we need to calculate the volume of a cylinder in the soil. So we know the elevation at the top and the bottom is going to be poured in concrete, and we know that it's 6.5 feet in diameter. So if we take the difference in those elevations, we come up with 28.1 feet, and the diameter of the shaft is given at 7.5 feet. Remember how to calculate a volume of a cylinder. This is provided in section D. If you look at D8, you'll see the formula for a cylinder there. So it is pi times r squared times the height of the cylinder. So we're given the diameter, so we need to divide that in 2, and then we can square it and multiply it times pi and the height of the cylinder. So here, remember, our pi is 3.1416. 3.75 squared, and then times the length of the shaft. Ends up being 1,241.4 cubic feet, and then we're going to convert that to cubic yards, which happens to come out to an even 46.0 cubic yards. That is just the shaft and soil portion of the pay item. Next, we're going to determine the volume of concrete in the drilled shaft and rock. Again, we got elevations here, so we take that difference. It's 32 feet. Notice that this diameter is a little bit less because there's a different bit that comes down to drill into rock. Again, use our formula, pi times r squared, height of the cylinder. In this case, we got to divide 7 by 2 and then square it times 32. And we end up with 45.6 cubic yards of concrete, shaft, and rock. So to summarize our solution per Article 516.16, we have our drilled shaft and soil, which is 46.0 cubic yards. And then we have our drilled shaft and rock, which is 45.6 cubic yards. And that would be our payment for these two pay items. There are a number of standards that contain information on cubic yards in the details, and you can either use the detail as is, or you may have to take that general cross section times the length to calculate the amount of concrete. In doing so, on such things like an outlet, you basically need to reference the section being used on the plan and that it came from the standard and how that is calculated. So in this case, we have an outlet length measured from the end of the radius. We got 16.6 feet. Is unique to your project. You know how many cubic yards per foot, so you need to multiply that. That gives you 1.15 cubic yards. The section AA to EE is from the standard that's given to you. So then you just need to simply add those together and come up with your total cubic yards. That becomes your quantity. Evidence of inspection, again, look in the project procedure guide or in the documentation guide for what you need for a concrete item. In this case, a daily plant report, a ticket, and an appropriate test. Here's an example of how the standard gives you the information. And you have to make sure you have the correct standard for the curb and gutter or outlet or whatever the case may be. And then it gives you the appropriate quantities for different sections. So in this case, for section AA to EE, you're giving the totals for different thicknesses of pavement. So make sure you correctly have the right thickness that you're using. And then for a length of FF, you need to measure that in the field and calculate the cubic yards accordingly. In the case here, you have thicknesses, so you'll have to also do a depth check to ensure that you are getting those thicknesses.